Am I audible, Tejashi?
Yes, sir.
Okay. Okay, we'll start. Only you are here today. So, have you watched the this week's videos? Yes, no.
Yes.
Okay. So we'll start today with again some very basic theories of DC machine. So this is the DC machine. Okay. What is this inner thing? This inner round thing. What is this called? Okay. This is called rotor, and the winding on it is the armature winding, and the outer ones is the field. They have field windings on it. All right. So the first thing we will start today is armature reaction. We will mostly talk about armature reaction. So what is armature reaction? Armature reaction is the effect of the armature magnetic field on the main field, or the field winding of the machine, of any machine, not only DC machine. Say the effect of armature magnetic field on the permanent magnet fields of a PMSM or BLDC machine, that is also armature reaction. So suppose the thing that I have drawn here is a DC motor. Okay, DC motor. So DC motor means what? We have given electrical excitation from outside, that is the armature is already carrying some current, and because of that the machine is generating a torque. That is, the current is the cause here, and the motion is the effect here. So this what are these squared things? Can you tell me what are these squared things here? These squared things perpendicular to the field, these are the brushes. So at the brush axis there is no current flowing, and the conductors carry opposite direction current on the other side of the brushes. So if, let us say, the currents flowing at this side of the conductor are all cross currents, then the currents on the other side of the conductor are dot currents. Okay, so this is the current that has been introduced to the armature circuit of this DC machine from outside, and as a result of that, this DC motor is rotating. Now the question is, in which direction is the DC motor rotating? So can you, from here we have the current direction, we have the magnetic field. From here, can we comment in which direction the rotor will rotate, clockwise or anti-clockwise?
Clockwise.
How do we know? So let us take this conductor. This conductor here we are taking, okay? So this is the conductor, and the current is cross. Cross means current is flowing away from us. So a positively charged conductor is flowing away from us, and there is a magnetic field B. So this is the velocity V away from us, and this is the magnetic field B. Now we know that force on a charged particle moving inside a magnetic field is Q into V cross B, right? So to know the direction of motion, for the direction of motion, to know the force on the moving particle because of this field, we have to apply this right hand thumb rule. So V is away from us and B is from north to south. I will draw B with blue. So B is flowing The B means the magnetic field due to the field winding. B is flowing like this. They are horizontal. In the way we have drawn, they are horizontal. Coming out of North Pole, going into South Pole. This is the B of field. Let me write BF. Now B is flowing in this direction. So if I apply right hand thumb rule, how is it? So it is like this, right? Yeah. So this conductor will experience a force downward. Experience a force downward. Correct me if I am wrong. Okay. I think I'm not wrong. Yeah, this side. Yeah. So this is so if the force on the positively charged particle is downward, there are several such particles in this conductor going in this direction. All of them are experiencing a force downwards. So basically, all these conductors on my left hand side are experiencing a force downwards. Hence, the machine or the armature will rotate in this direction. You can verify it by finding out the direction of force on a conductor on our right hand side. You will get it's upwards. In one class, maybe in week 7. Yeah, in week 7 we discussed such problems. Anyway, so the armature is rotating in this direction, but we know that in DC machine, this current direction is like if you look at the rotating armature from outside, it is rotating, the windings are rotating, but the current distribution, that is you have left on your left side cross currents, on your right side dot current, that never changes because of the brush. At the brush, the commutation happens. Commutation means change of direction of current. So we will always have current flowing like this, irrespective of the position of the rotor. Now, the field winding, they have some direction of field. But the thing is, the armature is also carrying current. It will also have field. So what will be the direction of armature field? We will look piecewise, like for every conductor we will look. So this is the main field, okay? This is the main magnetic field. I will in this direction. Now, let us take, say I will draw it green. Let us take this conductor. So this conductor is carrying a current, so it will create a magnetic field around it. So it is the current is going in, so the magnetic field around it will be in this direction. So you see, the magnetic field created by this conductor is actually aiding. Aiding means helping. Aiding means helping. Helping the magnetic field created by the main field of the motor. Similarly, if you do it here, again you will see it is in this direction. Field is in this direction. You see, all the conductors on the upper half, if I draw it like this, all the magnetic field created by all the conductors on the upper half are actually aiding or helping the field created by the main field of the motor. On the other hand, if we look at a conductor on the lower half, it is again creating a magnetic field in clockwise direction. Right hand thumb rule you can apply and you can find out. But you see here, the direction is opposite. Can you see? It's anti-clockwise. It's rotating in this direction, so it is opposing the magnetic field of the main field or the field winding. So what we have, say in this direction, in this region of the field, we have strengthening of the magnetic field. Strengthening means increasing because they are additive. The main field flux and the field of the field winding and the magnetic field of the armature winding, they are added to each other. So it's strengthening happening. On the other side, in the lower half, they are opposing each other. So what is happening? Yeah. So on the lower side here, let me use other color. Let me use blue. On the other hand, here they are opposing each other. So the armature flux is weakening the main field. It is weakening the main field. So let us look at the other side now. If we look at the other side again, here we have a conductor. So let us take this conductor, and it is creating a magnetic flux. If we apply right hand thumb rule, anti-clockwise. So anti-clockwise means this direction. Is it clear? This direction. So again, this is also in this direction. This one also in this direction. So you can see in this area, on the upper half of this pole, there is weakening. There is weakening. In this area, the armature magnetic field is weakening the main field of the machine. It's weakening here. Similarly, you can find out that if you see here, it is again in this direction, it is strengthening. Here the armature flux is strengthening the magnetic field. So let me complete the drawing here. So strengthening is happening, right? So we have weakening here, we have strengthening here. So you see, let me draw this figure once again. So a clear figure we have. What we had all the currents flowing in this fashion. Cross here, I should have drawn it before. Okay, anyway. And all the currents on my right hand side are dot. It doesn't matter whether the rotor is rotating or not. They will always be like this. The current distribution will always be like this. And we found out that it will rotate in this fashion. Let me copy this. We might need this later. Yeah. So what did we see? We saw that on the upper half there is strengthening. So I will again write. So I am writing say strengthening, S for strengthening, S for oh no, there is south pole also. So I am writing additive. Okay, plus for strengthening, minus for weakening, plus for strengthening. Right. So what do we see? We see that in motoring mode, now we will name the tips of the pole. So this pole, say let us take the north pole. The north pole has two tips. One tip is this one and the other tip is this one. You see, the rotor is rotating in this fashion. So the rotor, say one conductor of a rotor, it is seeing this pole. Say I call this pole as this pole tip as tip number 1. It sees tip number 1 first, then it sees tip number 2. So the tip that it sees first, it is the trailing tip. Most probably it is the trailing tip, because it is towards the back side. The rotor is rotating in this direction, it is towards the back side, so it is a trailing, whereas this is the leading tip. So what we have is, we have on the north pole, what we have on the north pole, we have in the leading tip, we have weakening, whereas in the trailing tip, we have strengthening, right? We will see what happens at the south pole. So it is rotating in this fashion. So this is the leading tip in the south pole, and this is the trailing tip. So at south pole also we have the same thing. We have weakening on the leading tip and strengthening on the trailing tip. So basically we can now generalize that for motoring mode, flux, the main flux is strengthened at the trailing edge of the pole, whereas on the trailing, on the leading edge we have flux weakening, and this strengthening or weakening is happening because of the armature flux only. Okay, now we will look at some terminologies quickly, then we will see what is the effect of this weakening of or strengthening of the magnetic field. All right, so suppose there is no current in the winding. When there is no current in the winding and there is only this field, this so this is the field. I was drawing with blue. This is the field, main field. So if the main field is horizontal, perpendicular to it there is no field due to the field winding of the machine. So this is called MNP. What is MNP? MNP is magnetic, is it MNP or MNA? I think MNA, not MNP, MNA, magnetic neutral axis, not MNP, magnetic neutral axis. And from the geometry of the machine, this is also called GNA, geometric neutral axis. Along the brush it is defined, geometric neutral axis. So when there is no armature current, this GNA and MNA, they coincide with each other, they are the same. But what happens when there is armature reaction? We will see. So I will draw the same picture once again. Now let me draw it here. Okay. So what we saw is we saw strengthening in this region, and we saw weakening here, we saw weakening here, we saw strengthening here. So basically now from this area, I have large flux flowing. I have large flux flowing magnetic field, which reduces here. On the other hand, here I have large flux flowing, which is reducing here. So previously, the magnetic field due to the field winding of the machine was perfectly horizontal. It was perfectly horizontal, like this. But now it has changed. Now we have more flux here and more flux here. So it has not changed, it has now shifted like this. From here to here it has shifted. Sorry. So now the field flux is flowing like this. Why this shift? Because of the current flowing in the armature. Right? So what is happening? This N is no longer my north pole. This S is no longer my south pole. I can hypothetically say that my north pole has shifted here. My south pole has shifted here. And the axis which is perpendicular to this flux, although I'm exaggerating, the shift might not be this large, is MNA. And GNA, geometric neutral axis, that is defined from the geometry of the machine, that cannot shift. So you see, under armature reaction, the magnetic neutral axis shifts from the geometric neutral axis by some angle theta. Okay. All right. Let me verify it once again. Just this direction and this right. Okay. So, any question till now that the main magnetic field axis of the machine has not changed because of the armature flux? Is it understood as of now? If so, then we will see what are the ill effects of it. The thing is, see, as I told you, that commutation occurs at the brush. So all the conductors on my left side, you can write it right. All the conductors on my left side will always carry a current in cross direction, means away from us. So they can be assumed to create a current sheet which is stagnant, which is stationary. This discussion we had in the very first session of DC machine, that the fluxes, armature and field fluxes must be stationary with respect to each other so as to create a steady torque. Since in this case field is stationary, so armature flux must also be stationary. So this is on my left hand side, I have a current sheet. On my left hand side, I have a current sheet which is carrying current away from us. On my right hand side, I have a current sheet which is carrying current towards us. So basically, this armature as a whole is creating a magnetic field which is downwards, right? As a whole, it is creating a magnetic field which is downwards, BA. And we saw that BF, the magnetic field, due to the field or the main field winding of the machine, was left to right when they are considered separately. Now, if we try to find out the resultant of these two vectors acting at the same place, you can find out the resultant. So the resultant, let me draw it with some other color. The resultant is this. So you see here, whatever we got from our discussion on armature reaction is nothing but the resultant of the two fields acting on the same place. Obviously there will be a resultant field what we can see at the end. This is the resultant field, right? So we have a magnetic circuit. Now we are going to analyze, what are the effects of armature reaction. We are going to qualitatively analyze. So what we have a magnetic circuit. We have a magnetic circuit, just like an electrical circuit. Have a magnetic circuit. We have two B fields, or we can say two MMF sources, right? MMF sources. So, and we have to find out the net effect. So there is a theorem called, you must have heard and used also, called superposition theorem. Superposition theorem means if you have multiple energy sources in a system, you can consider them one by one, keeping the others inactive, and at the end you can add up the result to find out the net result, find out the final result, whatever. But there is a criteria of the system, that can be any system, not only machine, circuit or any other system. There is a criteria which must be fulfilled so that we can apply superposition theorem. What is that criteria? Can anyone tell me? The system must have some property, then only we can apply superposition theorem in the system. Okay, the system must be linear. System must be linear. So if in an electrical circuit you have a resistance which is proportional to the current square of the current flowing through it, you cannot apply superposition theorem in this circuit. Superposition theorem means, say, A time fx plus B time fy. Am I doing it correct? No, okay, maybe there is something other I forgot. Anyway, what was that? Yeah, I think so. It is A time fx plus B time fy should be equal to f into ax plus by. Yeah, something like this. This might be wrong. Okay, let me erase this. So basically the thing is, whatever effects we have on the system, they can be added, they can be multiplied, but the system must be linear. Then only we can apply this superposition theorem. So now the thing is, we have two sources of MMF here. One source of MMF is the armature, other source of MMF is the main field of the machine. But my question is here, can we apply superposition theorem? Or if we can do, under what assumption can we apply? Under what assumption can we apply? As I said, that the system must be linear. But the question is, where from will non-linearity creep in to a machine? Any idea? Anyone can guess? Or in any magnetic circuit, what is the source of non-linearity? I gave you an example that if the resistance of an electrical circuit changes, that becomes non-linear. So very much equivalent to this non-linearity, how it can creep in a magnetic circuit. Problems are not important. It comes from the nonlinear BH curve. It comes from the nonlinear BH curve. If it so happens that there are two MMF sources, okay, source 1, source 2. When we analyze the effects for source 1, say it operates somewhere here. When we analyze the effect for source 2, say it operates somewhere here, and say the net effect is somewhere here, say the whole thing is in the linear zone, we can apply superposition theorem. But if we see that the addition is going towards somewhere here, or maybe one of them itself, or maybe both of them are operating in the nonlinear zone, we cannot apply superposition theorem. So that is what it happens in a DC machine. We always design machine so that it operates close to saturation. Why so? So that the machine is small. I can make the machine operate very much below the saturation level, but the machine will be very large and my iron will be less utilized. So this machine was designed such that when the rated flux flows through these poles, they operate at their very close to the saturation point, maybe say 1.3 Tesla, somewhere like this, the standard value for electrical steel, somewhere near this. But the thing is, now the armature flux is adding up with it. You see, when we have two vectors, one like this, other like this, you add up, sorry, a little larger, you add up, the overall effect is not changed. Overall effect is not changed. But here we cannot add up like this. Why? Because as soon as we have a strengthening here, the iron at this part is saturated. The iron at this part gets saturated. Whereas this iron, this part that say previously it was working somewhere here, it comes here. So there also the linearity is not maintained anymore. The linearity is not maintained anymore. So we cannot apply superposition theorem. Or in other words, we cannot say that although there is armature reaction, my total flux is same. We cannot say. Right? You can argue that I had armature flux here, I had field flux here, I had armature flux here. It is just added up. So why should there be a problem? The problem is that adding them up has caused a nonlinear effect in the magnetic field, in magnetic circuit. The circuit has got saturated at some places. As soon as the circuit saturates, what happens is, so BH curve, if you see here, the mu value is quite large. Thus, mu value here is quite small. So as soon as magnetic circuits tend to saturate, the reluctance of the circuit, which is L by mu A, this increases. Mu is dropping with increasing H. B equals mu H. With increasing H, we can see the slope is dropping, hence mu is dropping. So reluctance increases. When the reluctance increases, for the same MMF, we know that MMF is flux time reluctance. So when the reluctance increases, for the same MMF, our flux must reduce. So if you do a vector addition of the two MMF, the MMF of the armature and the MMF of the field, then if you find out what should be the total flux as a resultant of this, you will see it is less than what you actually have in the, what you actually have in the motor is less than what you calculated. Why? Because of the presence of this non-linearity. It has reduced, it has increased the reluctance, so for the same MMF, the flux has reduced. Any question till this? Everything is understandable. That's quite good. So what we have? We have now a lot of flux lines concentrating in this region. And very few flux lines flowing here. Similarly, lot of flux lines concentrating here and very few concentrating here. So our main flux is now flowing like this along the resultant what we showed there. Our flux is now flowing like this. Okay. Flowing like this. So what we got first what we got is that the net flux of the machine reduces. Flux of the machine reduces. We know that back EMF E is K phi omega, right? So if I have, say, a DC motor, it is connected to some supply. The supply is providing some current I. This is E. In this, if this is the terminal voltage, this is E. So whatever current, you see, this is nothing but like a battery charging. Current flowing against the potential. So basically this armature is absorbing electrical energy. So the power is EI. Now keeping everything same, if the E reduces, I cannot force more current because there is a thermal limit, the windings will burn. So if the E reduces, because of this armature reaction, for the same current, I am getting less power. For the same current, I am getting less power. So my efficiency is reducing in DC machine. In case of AC machine, we can say the power factor is reducing. For the same current, I am getting less active power. Okay. So that is the first ill effect of armature reaction. We will look at other ill effect of armature reaction. But before that, we will look a bit towards the commutator. Commutator. Before we go for commutator, can someone tell me what does the term commutation means in electrical engineering? Commutation most probably means transport, bus, tram, etc. But in electrical engineering, commutation is also transport of current. Say, for example, you must have studied diode rectifiers. So when one diode turns off, another diode turns on, the current commutates from this arm to this arm. We call this commutation. So this commutator, what does it do? It helps in commutation of the armature winding. Commutation means changing of direction of current in the armature winding. So let me quickly draw the developed view of a commutator. What is a developed view? We have already discussed in the very first class of DC machine. There is a developed view of commutator. Now suppose we have windings connected like this. I should have drawn somewhere, okay. So like this, the windings are connected. Okay. Now there is a brush. There is a brush here. Say here. Okay, let me first draw it like this. There is a brush here. The width of the brush is same as the width of the commutator segment in this fashion. Okay, now what is happening? Some current is coming from this side, some current is coming from this side. As we saw here, that one side of the commutator current direction is something, other side it is opposite. So if on the left side current is coming this way, the right hand side current will come the other way. And the net current is going out through the commutator. There is connection. There is the brush. We have connected our conductor in the brush, and through the brush the current is going out. Right? We know that when the conductor is just in front of the commutator, there is no current through it. Why? We have discussed in week 7, you can see. So there is no current. Or in the week 0 lecture also there is only 2. So why is there no since there is no current in the winding flowing through the commutator, what we can do is, say our brush is here. So the winding close to the commutator, the winding close to the brush is having no current. Now you look at this winding, forget everything else, look at this winding. I will draw it with black. Look at this winding. Its two ends are connected at these two brushes. These two commutator segments. And this commutator segment is short-circuited by this brush. This brush is a conducting material, graphite or something. So it is short-circuited. A winding in a machine is short-circuited, but that is not causing any problem. Why? Because this is in any way at the magnetic neutral axis. It is not carrying any current. So a coil that does not have any voltage induced in it, we can short-circuit it. No problem. But the point is, where did I draw? But the point is, say in this diagram, now our magnetic neutral axis has shifted. So we have no more, so this current distribution that I draw here and that I drew here is no more correct because the magnetic neutral axis has shifted. So now what will happen? Now this winding here and this winding here, they won't carry any current. This winding here Why? Because the windings do not understand where the brush is and all. They understand where is the magnetic field, in what direction it is rotating. In that fashion, it will carry the current, right? So we have crosses here now. No current here, dots here, and dot here. This will no longer be cross. I hope it is understood. If not, tell me. Sorry, I was drawing black. So we have dot here. We have dot here. So you see, our current distribution has moved with the magnetic neutral axis. That is not surprising. The armature flux will always be along this. So what we had previously? Previously we had a current sheet. Let me draw with this. Previously we had a current sheet like this. Now it has been rotated. Now the current sheet is like this. Sorry. Now the current sheet is like this. Let me draw on it itself. Like this. But the problem is my brush was here and the brush is still short circuiting the adjacent commutator segments. Previously, when we say if there was no armature reaction, that was perfectly fine. But now I cannot put the brush here anymore, because this conductor that I drew with black is now no longer inducing zero voltage. It has some positive voltage. Some other conductor here, which is along the magnetic neutral axis, that now can be short circuited, right? That is not having any induced voltage in it. Or in other words, I have to shift my brush from here to here. So if I draw it in this, let me copy this figure anyway looks good. I hope everything gets copied. The fundamental is we shall always have the brush in our geometric neutral axis. Previously our brush was here when we did not consider armature reaction, or we did not know about armature reaction. Now we know about armature reaction. We know that we cannot keep our brush here anymore. We have to shift our brush so that the brush is always short circuiting a conductor which is not carrying any current. Otherwise, what will happen? Otherwise, there will be sparking. You cannot short circuit a conductor which has a voltage across it. That is very much similar like short circuiting a voltage source or a battery, whatever. So now we have to shift the brush to here. We have to shift the brush to here. We cannot have the brushes here anymore. This is called brush shift. We have to shift the brushes. Now, I was telling you that this is an ill effect, but how is it an ill effect? Okay, there was a problem. We understood the problem. We found out the solution. We implemented it. We simply shifted the brushes. Then how is it an ill effect? Can someone tell me? How can brush shift be an ill effect? The ill effect comes from this fact. You see, suppose this is the field of the armature, the magnetic field winding. This is the field of the armature, perpendicular to each other. And I had the resultant here. Okay. I had the resultant here. No problem. So initially I thought that I should keep my brushes here, but then I saw that no, okay, I have to shift my brushes here. Oh, am I correct? The other way around. Okay, anyway. So this angle theta, that dictated our brush shift, how much we need to shift the brush mechanically. So what is the problem? We simply shifted the brushes and got rid of the got rid of the problem of the short circuiting problem. There will be no more short circuiting, no more sparking. There will be short circuiting, but no more sparking. We are short circuiting a zero voltage source. What is the problem then? The problem is the armature current is not a constant. If the DC machine keeps on supplying the same torque throughout its life, then there is not a problem. Then the armature will always have the same value of PA, armature field. But the thing is, the armature does not always carrying the same current. Say if you reduce the load, now reducing the load means the current reduces, so the field reduces. And the main field is not changed. It is kept the fixed. Armature, the load has reduced, so the armature current has reduced. Simple. So now the resultant has changed. Resultant magnitude has changed. That is not a concern. The concern is this: the angle has changed. It is now at some other angle. So I have to keep on shifting the brush depending on the load. That is not possible, right? That is not possible. That is why this is a problem. You cannot have a constant brush shift, and variable brush shift is not possible. That is the reason why brush shift is not a stable or steady solution for armature reaction. For this thing, people go for different kind of windings, extra windings on the field. It is there are two kind of windings. One is interpolar to go for, another one is compensating winding, right? So what is interpolar winding? We will see. As you can understand that interpolar winding will be present somewhere between the poles. That is why they are interpolar, right? So how would that work? We will copy paste that diagram once again and try to understand how would interpolar winding at all work. You see, we had our brush here. Because of armature reaction, the magnetic field shifted in this direction, but we do not want it. We want it in the same direction. So I have a vector like this. I am not much concerned about its magnitude, but I want the vector to be here. So what should I do? I should give a vector. What is happening? Just a second. What happened? Okay. Something is wrong with this. I cannot see anything. Just a minute. Let me turn on OneNote once again. It looks like I lost some things. I hope not much. Okay, we did not lose anything. We did not lose anything. Oh, sorry, I have to present once again. A tab, sorry. Window. All right. Sorry for the problem. Okay. So what I was saying, I said that, say I had this vector here, this vector number 1 here. I want it at this position. This is my desired position. So to do this, what I have to do? I have to externally add another vector 3, such that, say, my drawing, it comes in this direction. The resultant is in this direction. So if I draw the same thing here, can I have some other color? Yellow, can you see yellow? Okay, let me use this. So to do this, what we have is we have to have a vector applied externally, which will be a magnetic field applied externally, which will be acting in this direction, such that this and this, their resultant again becomes horizontal. This can be explained in other ways also, from the point of view of the flux waveforms and all, but this is an easy way to understand. So to do this, what should I do? I have to have a small pole here. I have to have another small pole here, right? Going out means this will be a north pole, this will be a south pole. Again, we will look at this problem. What I said that this armature current keeps changing with the load. So the direction of this resultant, this vector 1, also keeps changing. So if I have to have the resultant in my desired direction, horizontal, this 3 vector, this also must keep on changing its magnitude depending on the load. Then only I will always have it in the horizontal direction. A very easy way to make sure that this magenta vector vertically upwards, which is the interpolar axis, interpolar field, it has some winding on it, right? This winding is in series with the armature winding. Now, if this is in series with the armature winding, my compensation is now also adjusting itself depending on the requirement. My compensation is now also adjusting itself depending on the requirement. So now I have a very powerful solution. I have a resultant like this. I want it in horizontal direction. For that, I have to add a vector like this. But the problem is, this thing keeps changing. Sometimes it's small, sometimes it's large. But since I made such an arrangement that when this resultant changes, when this thing changes, this vector also adjusts itself, so that the whole resultant is always horizontal. This is how the interpoles work. No, interpole is not that interpole. International pole is interpolar. So they interpole. That is POL. This is POLE. Okay. So this interpole, this is how it works. There another winding that is called the compensating winding, but I don't think we will have enough time to discuss about it. Compensating winding. So what we have? Okay, let me draw the stator once again. So stator, previously we had poles, our principal poles. Now on this we have interpoles, small interpoles. Compensating windings are put here. Compensating windings, they are also in series. So slots are made on the pole face, and compensating windings are put here. They are energized in such a fashion that basically what my target is to make the armature flux 0 in the air gap. So they are put in such a fashion that they reduce it, so that we have a very small resultant armature flux in the air gap. And we have mostly the field flux in it. Okay, that's about it. I thought I will cover this problem. Don't worry, this problem will be covered by Siva next Tuesday or any Tuesday. What am I writing? Tuesday, 7 p.m. to 8 p.m. Siva will take class. There he will cover this problem and some other problems also. So make sure to attend his session. He will cover these problems. I have mostly covered the concepts of armature reaction and their ill effects and how to avoid them. Okay, if you have any question, I will answer to them, or else I will conclude today's session. No question? Okay, then I will conclude. Thank you for joining. We will meet next week once again at 7 p.m. next Saturday. Bye bye.